So now I'm going to do another example for multiple regression. Sorry about that. So what happens when the model is not statistically significant? All right, sometimes you will try to run a model and it's just not good and you can't really do anything with it. And I want to show you that because sometimes a lot of people will try to run the model and it's not good and they'll keep using it. There is something you can do when the variables are not normally distributed and your model looks bad. You can do something called transformations. We're not going to cover it in this class. If you ever get curious about it, go find a book on regression and it'll talk about transformations and it'll walk you through it. We don't have the time to do the in-depth analysis that we need to so that I can make sure that you understand it. Because it's kind of, you can do transformations for different things and different transformations for different types of variables. So, okay. So now I'm going to use another data set. Here's the link for it. It'll be in the PowerPoint. It's for cement composition. So a material scientist studies the heat that's generated in cement mixtures. The scientist varies the 4 ingredients in the mixtures to assess the impact of overall heat generation. So heat evolved is my response, and that's the amount of heat that evolves in a cement mixture. X1 is the amount of tricalcium aluminate. X2 is the amount of tricalcium silate. X3 is tricalcium ammonia ferrate. And variable 4, which is X4, is dicalcium sulfonate. So all these are they're different compounds and they're testing them, and those are the predictors. So I have 4 predictors and 1 response. Okay, again, got to remember those assumptions. You should have independence of the residuals, no multiclinarity, no significant outliers, high leverage points or high influence points, and your residuals should be approximately normal. All right, so again, I've got the directions on what to do. So let's go do it. I'm going to go run it. Okay. So I've got my variables down here. I'm going to go stats, regression, fitted regression model. So my responses were heat evolved. My continuous predictors are X1, X2, X3, and X4. And again, it always helps to look at your data. Let me show you if I go back and look at my data. You can see these are all just numbers and there's no categories to them. They look pretty good. So I'm going to do that. There we go. Stats, regression, fitted regression. Okay, so my response, and then I'm going to do my continuous predictors because these are continuous numbers because you can see some of them have decimals. I'm going to do my graphs. I'm going to do 4 and 1, and I'm going to add my residuals for X1, X2, X3, and X4. So I'm going to hit OK, hit OK. Okay, first thing again, what I see, and I'm going to make this smaller so we can see more, and I'm going to bring it in a little bit more. Oops. All right, so I have my regression equation. Heat evolved equals 62.4, and then it has 1.551 for X1, 0.510 for X2, 0.1023, and all that. So again, if I had a value for X1, X2, X3, X4, I could plug it in and get and estimate the heat evolved. All right, but let's go here and look at my p-values. Ooh, that's a huge p-value for that whole equation. It's 0.399. And if I think about comparing that to a level of significance of 0.05, there's no way it's going to be significant. There's not going to be a relationship. So then let's look at X1. X1 still has a high p-value, but look at that VIF. It's 38. And remember, I said anything over 10 was high. So that's really high. X2, 0.501, same thing. Look at that VIF, huge. 0.896 for X3. Again, high p-value. Same thing for the VIF, for X4, and then for the VIF. Okay. Well, look at the R squared, though. The R squared is spectacular. I mean, it's 95.94, and the S is small. That's great, but look at those p-values. I can't use them. Those p-values are enormous, and so are the VIFs. So there's something going on that's making it, not be a great model. And let's go back to one thing in this model. If I go back and look at all the names of the compounds, look, here's tricalcium. Both of these have tricalcium in it. This one has tetracalcium, and this one has dicalcium, and this has silicate, and this one has silicate too. So something's going on with these chemicals. Because look at my VIFs. They're just saying these are really high. Something's going on. And look again. It was showing something with 2 and 3. And look, silicate, that's it. I think that's problem. These chemicals are too similar. So there's really no way we can see what's going on. Okay, now if we go down here though, our regression looks better. Our regression does have a 0.00. So that means as much as my constants up here was 0.399, it's saying that the model is significant, but look at all my p-values in my VIFs. I don't think it's good. So then let's look at our residuals. Here's my normality plot. There's a couple of points not on the line. This looks okay. It's pretty, scattered. This, it's not great. That really doesn't look like a normal distribution. It looks like I almost have like a binomial. Here's a length and here's a length, and then it's really not normal. And again, don't worry about that one. So look here, my residuals, those aren't really that spread out. Those are okay, and those are okay. All right. So if I go back up, and then that one's okay. So the residuals look decent. Normalities, okay. I didn't have any residuals that were large or anything. And it did show the model was significant, but the problem was when I looked up here was look at those VIFs. Those VIFs are huge. And none of these were significant on their own. So you got to be mindful of that. So when you write it up, you could put while the p-value was significant, none of the individual variables were significant, and the VIFs were unusually high. So that's how I would say that one. And you could also explain that because there's so many different, the chemicals were very similar, there's something going on with that too. Hope this helps.